Hello, everyone. Thanks for joining us for this Stardog webinar. My name is Ingrid Ramos, and I'm a Director of Marketing here at Stardog. We do host a variety of webinars and demo days featuring subject matter experts in data management, typically with a focus on implementing flexible data architectures using knowledge graph. You may hear this being referred to in the marketplace as data fabric, data mesh, semantic layer, pick your nomenclature, but our goal really is to share how a flexible data layer often serves as the missing middle to data architecture between where your data is stored and where it is consumed in order to help you future-proof your data management practices. Today's webinar will be a full-length webinar. Just to say, I know we often have our demo days, which are a little more focused on product. Today is going to be focused on some best practices, as well as a Q&A here at the end. The topic is going to be unlocking the next level of manufacturing value with a knowledge graph, and it will address issues in modern day manufacturing and manufacturing adjacent businesses. We've heard many folks in the manufacturing community and beyond just coming out of lessons in the pandemic and heading into what might be a potential recession, really preparing and addressing their stack and their data management practices and asking, how can we prepare for disruption, given disruption really is the new normal. And so our speaker today is really someone at the forefront of helping customers prepare for these challenges. That is Al Baker, the VP of Enterprise Solutions here at Stardog. Al has helped several top organizations transition their data practices with knowledge graph, and he's going to share some of those best practices and examples and use cases with us today. This webinar is being recorded, and a copy of it will be sent after the event. We ask you to go ahead and use the Q&A tool to ask questions. You can also use the chat tool. I will be monitoring that as well. And we'll probably serve some of the Q&A up at the end, but if you have any issues or questions, feel free to ask them throughout. With that, I'm going to go ahead and kick it over to our speaker. Over to you, Al.
Thanks, Ingrid. All right, so today we're going to talk about manufacturing and how you can unlock the next level of value with a knowledge graph. This is an area that my team is looking at, especially this quarter, understanding lessons learned across a number of our different engagements and going to market, sharing those lessons learned, offering things like templates and other solution accelerators that we'll see later today. So we're going to do a quick treatment on the promises and challenges of Industry 4.0, understand how Stardog and knowledge graphs fit into that representation. In particular, we're going to take time series as an example, not only how it's represented in the knowledge graph, but how we can take advantage of features like logical inference and classification, and then take the analytics from that and move it through a machine learning model and show how this all works together nicely. So Industry 4.0, the fourth industrial revolution, means a lot of things. And what we wanted to do was take a step back and look at how it's being portrayed in terms of the value in different areas. So there's this paper from McKinsey & Company on capturing the true value of Industry 4.0. And it looks at things like improving data and connectivity between the factory-related business units in the field, improving human to machine interaction, adding in the analytics, machine learning, and AI, as well as advanced production methods like 3D printing and renewable energy and things like that. And as McKinsey highlights here, as you go through and start to adopt some of these technologies for different use cases, you start to unlock value in all sorts of different ways, from things happening in the factory, like a control tower, to inventory management, improving the productivity of the labor force, decreasing the amount of downtime, or another way to say that would be increasing the uptime in the factory, as well as throughput in terms of what's being manufactured, improving forecasts, and lots of different use cases around cost management and quality. We'll touch on a few of those today. We'll also look at this in the context of a few different verticals. So we could take the manufacturing use case. We'll see at least one example within pharma, and then we'll look at things that have engines. Now, within this paper, McKinsey also mentions how, while there's a lot of value in this area, there are enterprises that get stuck, right? They have get stuck in a purgatory, if you will, struggling to fully realize some of this capability and transform their efforts, and quite frankly, deliver a satisfying return on investment. And so the Stardog and knowledge graph angle is going to take a look at this in a way that they should mitigate some of those concerns and give a path forward on a repeatable approach to incrementally build that value. So I like to think about this in terms of how fast can we get the insight into the enterprise, meaning we want to be able to run these different experiments, these different analytics, compare as operated versus as manufactured or as designed. And we want to do that in a way that is not a fire drill or the result of bringing in the consultants, having our experts pour over data extracts, spending too much time in Excel. For those that have been on my prior talks, we'll often reference NASA here, and they did something similar and realized that they were spending way too much time of having their rocket scientists live in Excel as opposed to getting down to business on what are the different aspects, how does this analytic compare to another one, and so on. There's also a strong data challenge in all of this. And there's a large variety of different data models, data structures, everything from time series to the hierarchies found within bill of materials, recursive data structures where there is a material that could be a synonym for the product or assembly and in subassemblies and so on. There's standards in this area, like the ISA 8895 standards, and we'll talk about in a minute. And these all make the technical choices challenging in terms of how do we start thinking about where knowledge and insight comes from in the process, and how are we going to enable that, and quite frankly, where to start. So I like to show this cartoon here on thinking about the knowledge representations against a very, very high level process diagram. This one in particular is for pharma. It was published at the University of Pennsylvania on a oncology drug, and it talks about all different ways that the factory is planned, the ROI in terms of uptime, how much they need to make, and so on. And if we think about this, at any point along the process, there is typically going to be at least one model, and they're all going to kind of interrelate. So starting on the left, of course, we want to look at redundant supply chain models, thinking of the different impacts on changing a supplier, especially in the post-COVID world. How do we set that up so we don't have a single point of failure there? Bill of materials, bill of substance, and so on. And I'm using this term in the abstract sense. Obviously, there's different bill of materials depending on if you're in the factory or out of the factory, if it's on the purchasing side or the assembly side. Specific to pharma, there are different quality aspects coming in. This is called an assay. So I'll give you an example there. Calcium carbonate, same thing that reefs and things in the ocean are made of. If it's sidewalk chalk, you might have a one set of tests, but if it's going to be an antacid for humans to consume, you might add some additional tests, like we're going to screen for lead in the batch and things of that nature. Once we're inside the factory, obviously we're running batch models, producing lots of product, trying to then correlate that to some of the enterprise control. And so what is this machine actually producing at this given time? And quite frankly, a lot of the machines will not have that specific, right? It's in use or not in use. So if you correlate based on time, you can find out, yes, this is the machine that was being used to produce this product at this time. I know other manufacturing execution systems do kind of keep that foreign key around and have some traceability in there. But this is all relatively standardized, and it does refer to a lot of these models around it, right? The purchasing model, the customer, the order that's being satisfied, the product, and you might have a different view of the product from the product as it's described in the commercial efforts versus the product as defined within the manufacturing effort versus the product as it had been defined during the engineering or design phase. And then as soon as we exit the manufacturing process here, we're back into inventory management, supply chain, and in this case, if we're talking pharma providers and patient models and things of that nature. And so I like to show this graphic in that along this continuum of processes, the key point here is not necessarily you must start on the left or somewhere in the middle. It's that there will be these different representations of data and different models. Some of them standardized, some of them might be specific to the manufacturing or engineering tools in play. But wherever you start, you can always take that next hop, that next question of how does this relate, upstream or downstream? And this also is good for fueling that conversation around which use cases are we going to be looking at. So if I think about those challenges and the different data models in play, then we're looking at a standardized approach within the knowledge graph space where we want to accelerate that insight, meaning we don't want to wait until there's an issue that we stopped the shipment and some of it went out to customers and they found that the engine was knocking in cold weather. We want to find that sooner than later because it's much cheaper to fix something before it got shipped. It's even cheaper before that to fix it when we were designing the factory. And it's even cheaper to fix that when it's the drafts of engineering or design efforts. So moving that insight as far left as we can get it is critical to the agility and cost savings and revenue producing use cases within this general Industry 4.0 initiative. And second, we don't want to just have this insight be something that is produced by a particular one-off data science effort or subject matter expert doing an internal study. We want this to be democratized and made available so it's enabling decision-making all along the different processes. So if we can see the related dependencies of a particular product, its ingredients, the things that go into it, how it's being assembled or manufactured, and that's available from everything from the manufacturing control tower to someone on the floor to the supply chain practitioner that is managing inventory, then those businesses will have a clear advantage over ones that are more reactive, right? That, wait until someone blows the whistle and stops the line to investigate the issue and so on. So if we can move that up, then what we're going to find is a flywheel effect as wherever we started along that continuum of knowledge representations, as we make those additional next hops along the way, we're going to be unlocking all sorts of different use cases. Stop shipment is one, prognostics, real-time reporting, or operational excellence in terms of, if we're going to do training for a vehicle, what is the best way to train on that vehicle? What's the impact in terms of how it's performing, in terms of engines and things of that nature? We might unlock predictive maintenance. So instead of running something to failure, then replacing, instead run it essentially to a maintenance cycle, in which case we can replace a part before it breaks and has potential other side effects. And then, of course, there's the supply chain side, understanding what inventory levels we're having, input coming in and its dependencies into the factory to supply chain on the outbound side as well. So our approach follows the standard practice that we like to talk about here at Stardog in terms of identifying a use case, then building a knowledge model by understanding what are the key entities and relationships supporting that business process. And with that knowledge model in hand, we'll then align the existing data systems to that model. But there is one key difference here, something that we're adding today that we just started talking about a bit last year, and we're looking at a whole lot more this year, especially as part of our manufacturing go-to-market. And that is, how do we combine the analytic pipelines with the knowledge model? So instead of having these be two separate worlds where one is a series of summary statistics based on how the factory's performing or the products are performing, we want to be able to take those and bring them into the knowledge graph so that we can classify them, add them into our knowledge representations, build and compose off of them. And we'll see more of that today. And then last but not least, the whole point here is not just to have the world's best manufacturing knowledge model, but we want to democratize the data usage across different personas, from enabling those data scientists and statistics practitioners to analysts, executives looking at executive dashboards, to any other citizen data user that if they had a bit more standardized representation of the information and they could find that kind of next dependency, that next top, then they're going to be way more productive than if they didn't have that. So within a enterprise architecture, what does this look like? Well, we like to say this is going to be a semantic data layer, and this will have that connected knowledge graph of those defined entities. And a nice way to think about it is it's not necessarily just one graph, but could be a series of graph models that interrelate. And that will be a recurring theme as we kind of get into the details here, because each one of these, you can deep dive on pretty far. So in this example, we've got a vehicle model, our engine sensors or telemetry coming off, so our digital twin, third-party data sets like weather and pollution, both the product and supply chain models, as well as our customers and their orders, the warranty claims they make, and things of that nature. And you can see here that our semantic data layer is not just powering a single application. I'm not here just to talk about Stardog Explorer as the one key enabler application, but it's going to be a series of applications, analytics, reports, system-to-system data sharing, and this will produce all sorts of applications and user interfaces within the business. This also matches how we've seen customers mature over time. I'll mention NASA again, where they started with what was essentially the precursor to Stardog Explorer. It was called Polaris, and that provided the ad hoc data browsing, and have since expanded to include a semantic search application, a avionics traceability and sign-off, automated reports, and I'll call it engineering tools in terms of understanding change impact, especially on the large scale. Now, this is all going to be a layer that is unifying and connecting the dots across the data assets available. And this could include traditional data warehouses, raw data lakes or the enterprise lakehouse, operational data stores, unstructured or structured data in all forms, which could be itself being unified over systems of record. So the implication here is that we're not necessarily going to connect our knowledge graph platform directly to the manufacturing execution system, but as these systems have their data organized into warehouses, we are going to leverage the semantic layer to connect those dots and get us that insight. So what is an enterprise knowledge graph? What is connecting these dots? And it is essentially a software platform that's going to unify both the data and metadata using semantics and inferencing. So it's not only connecting the dots from, this product has this part and this part was built from this assembly with these subassemblies, but we have descriptions about the metadata itself. So we have that schema level descriptions, and that's key because that's going to let us do things like harmonize different definitions. I kind of picked on material earlier, in that quite often material will be kind of the epicenter of manufacturing, but it can mean a lot of things, from the actual product to all the materials that go into it. It can mean assembly and subassembly and so on. And so having the different descriptions there helps us tie that together, and then will enable us to navigate that structure. So if we do need to drill down, we can get there. Likewise, if we want to kind of go horizontally and think about the inputs and outputs in terms of producing that material, we can do that as well. And just as we looked at the knowledge models and how there's always a next hop to make, so too does your enterprise knowledge graph serve as the platform to evolve, bring in additional data sources, and organize it in a way that it is that graph of graphs that is being assembled, things linking to each other. And that should follow intuitively as a reasonable process, such that, if you're doing quality and looking at quality notes and deviations, that shouldn't impact others doing the product catalog and product 360. And even though they might correlate, the quality notes will be about the product, but we want to be able to build these knowledge models independently, adopt them in a unified platform where those connections and cross links are available in place. So looking at the layers here, obviously this is a simplified diagram. We've got apps, AI, and BI tools up at the top, and the different data silos, which could be different databases in a common platform like a data lake or lakehouse. But the point is that we're connecting those dots, enriching it as we go, bringing in that semantics and the schema definition around the metadata incrementally. Now, if you're not familiar with Stardog, I'll quickly mention that in addition to the core platform, which operates as that data middleware, there are a series of front-end tools that are available. These all come packaged with the Stardog Cloud user journey. So this is actually a screenshot from there. Explorer is our ad hoc data browser. We have Stardog Designer that lets us design those knowledge models and map them to existing sources. And then we have Stardog Studio, which provides admin and kind of lower level engineering integrated development environment for building out specific queries and things like that. And we'll see some of these as we go through the presentation today. There will also be a version of this, including the portal capability for on-prem customers in due course here. So how do we use this to connect the data and get to that insight? Well, we're going to look at the different data silos, and I mean that in a positive sense, in that they are typically built for purpose against their original use case, right? The manufacturing execution system that has the table of sensor readings is not being a bad enterprise citizen by not sharing its data, but it's built for purpose there. And then the sharing interface that it does promote will let us extend that forward. So looking at the different data sources, there are options to either ingest, virtualize, or cache within the Stardog platform. And this is that first step in terms of being able to represent the data source connection and provide that mapping that's going to turn tables and columns into nodes and edges. Now, the mapping itself is going to be referencing terms within that knowledge model. So looking at those different definitions and understanding, what do we mean by material, by assembly, by product? Are these the same thing? Are there subtle differences? We're going to enrich that along the way, which could be everything from harmonizing disparate definitions to having just a little bit extra compared to what's in the source system, right? So, this table is sensor readings, but it's all sensor readings on bar scans for inventory management. So we can say that this record is of type inventory record just by the fact that it's in that table. So it's a kind of static enrichment for that table, but otherwise moves us away from having to understand specifically, what does that column mean? What does this number mean? Oh, the 10-digit numbers come from the inventory system, and the 8-digit numbers come from the manufacturing system. With that graph model in place, we can then infer different relationships. And so the inference capability of knowledge graph allows you to express how these relationships come together, and you can layer on and compose that, right? So we have, here's an engine that is performing well might be another class called compliant, the compliant engine. And one that is able to do that in cold weather might be a cold weather compliant engine. And that can all be done just by these descriptions of how these different classes of information relate. We do not have to go tag our data. We don't need to have a crowdsourced data augmentation effort. We need only provide the description on how they relate. And then finally, once it's in that form, it's ready for analysis and consumption, democratizing that data. In particular, Stardog offers a series that we like to call front ends to the platform, both the standard Sparkle protocol support, but also a SQL endpoint that's going to be using high quality tables based upon that knowledge model. We've extended the Sparkle standard with path queries that let us do various types of searches, find shortest path and things of that nature. And then also GraphQL for those familiar with building front-end tools and interfaces of that nature, as well as a number of different APIs and programming languages. So this is all relatively standard in terms of our normal approach. But I mentioned before how we are going to augment our steps, in particular, on how do we take the analytics and elevate it into the knowledge graph. And so if we look at a data science workflow, we're going to augment that within 3 places. The first one is introduce knowledge graph queries as an input into the feature engineering, building the training data sets and so on. And this should follow because we have just invested in that harmonized, unified view of the world where data has now been connected. We can disambiguate different elements. We can make sure that when we're talking about members in the data set, that these are distinct members, not accidentally copies of each other. And so being able to leverage that within this data science and machine learning environments is very important. As the data science workflow occurs and the ML algorithms or analytics are run, they will produce results, predictions, classifications, different values. And if we can take that frame of results and connect it back into the knowledge model, then we have done an uplift of those analytic data points into an enriched knowledge graph. So now we can start to say things like, if these values are within a certain range, then we can classify this product as well-performing, or the engine is getting hot, or it's potentially risky, or all sorts of things, right? It's up to us to be able to take those business rules and codify them as logical relationships within the graph that are building upon the analytic values. And this is not only limited to being able to work within, I'll say, the lower level data science environment, but we can use tools like Stardog Explorer and the Advanced Query Builder to start to explore that data, be able to express our queries visually, and consume that in different ways. And we'll see that in just a second. All right, so that's the overall story on how we're approaching manufacturing. And now let's take a look at a particular use case. And so this is a digital twin use case where a manufacturer has sensors, perhaps some access to third-party data like weather information, analysts who want to see the performance of the product, and data science who wants to predict how that product will do in different weather conditions. If the product as designed is going to work well or not well, this could open up, the Canadian market or the Scandinavian market. And so our challenge is to find the ideal prediction model on that engine performance as designed to as operated in these colder weather markets. And the pattern that we're going to do to meet this challenge is what I like to say a good foundation for how to use an analytic capability and a knowledge graph together. Now we'll be doing this with Databricks, but the analytic is generic, right? We want to be able to do things like calculate the statistics and metrics over a time series and then save those results back to the graph. There are some clear benefits, by choosing Databricks and that we have a partnership with them. There's advantages there. We tie into the catalog and make building this much faster. But the principle is generic, right? We can apply this template to any combination of an analytic platform in combination with the knowledge platform. So once we get those basic stats into the graph, we will then build an inference rule to detect issues or compliance or other classification of what those statistics mean. And so again, here's how we take those analytical values, quite often tables of numbers, right? And then we're going to derive meaning off of them. We're going to pull in a data from a disparate source, in this case, a third-party series of weather readings, and see how that relates. And then draw that into that machine learning workflow we just looked at a minute ago. Take those values, store them, and then use the combination to evaluate if the profile of how we are predicting an engine will perform is accurate or not. So we're going to use this all together to answer our question. But we're going to use dynamic time warping. If you're not familiar with that, is essentially an algorithm that can elongate the x-axis. So if we have, an engine running for different time periods, how do we compare those? Well, if we elongate the x-axis, then we can compare two curves and we get a notion of distance between them. So our first step is to design the model. And the key thing here is not so much the individual topics in this example, but you'll notice that we have things about a vehicle with engines on trips, going through locations with telemetry data and weather reports and things of that nature. But off the side, we've got run statistics and compliance. And so the key thought here is that we can also represent the statistics directly in the graph. We can describe that with as much that we're going to use to track. So we'll be looking at some very simple things, mean, max, and min, but it could be anything, right? It's a knowledge representation of the analytics side. And you also note that these are not connected. I am not connecting run statistics directly to a vehicle. And that is because we should be able to connect this knowledge model to all sorts of different capabilities, right? The ability to generate some stats over a time series should be reusable. We should be able to apply that against all sorts of data, whether it's sensors in the factory, sensors in the field, or both. So let's take a look at a little bit more on how we represent that time series data. So here we've got a sensor, and it's going to be in a run. So this represents the actual series. We've got the value as a data attribute of that sensor. And then we're going to add that statistics node that, based on that series, let's capture the min, max, and mean. And this is a very direct model, right? We haven't done a lot of fancy stuff here. It's basically just the sensor readings in a series. And from here, we could do roll-ups and do aggregations. So if we wanted to take a time series and bring it down to every 10 minutes, as opposed to every second or every minute, we could do that, store that in the graph as well. And we're adding, most importantly, the stats nodes to their own named graph. So this could be a combination of a virtual graph that has the sensor edge, that sensor to series run virtually within the lakehouse. And then we are generating the run statistics and adding those to their own named graph. And the query snippet to the right shows exactly that. So this is from the full example, which we hope to publish as a standalone notebook that you can download and run. But we can see here that we got in our where clause things about the sensor, its run, the label, the sensor value, which is line 18. And we're going to then insert into this results graph, that's line 3, the mean, min, and max with a label. And then we will attach the run to the run statistics. So we will link those up. And that gives us essentially this pattern of using named graphs as our analytics space as we are building this out, right? So this is relatively straightforward, but you could have more advanced analytics that you're, changing parameters on. So you could have run parameters in here and capture that in the graph as well. And you might have a named graph for different analytics that you've built, or each one as you have changed the parameters, so that you can compare them, right? When I adjusted my parameters in terms of how I'm populating the where clause, here's how I produce the analytic or roll up on that. And this is the key insight that I'd like folks to kind of take away from this, is that we can combine the knowledge representation with the statistical representation and then combine them on the fly in the knowledge graph. So the next thing to do is start to codify the interpretation of those stats. And so here's where within Stardog Designer, we have the ability to introduce Stardog rules, and you can do this visually. So here we've got a max and min range, and if both of those are true, then we can infer that these run statistics are going to classify as compliant. And now that's going to add a additional node inference in our graph. So run stats will have a type edge to compliance. There's obviously a lot of things we could do here. We could classify, we could infer data property value, could infer links. But in this case, we're going to infer another class membership. But because it's in the knowledge representation, we could then extend this further. We could make statements about different types of compliance, different combinations of compliance and something else, right? So we're moving away from having to keep track of, like in a script or something, the individual analytic values, and we're moving that up into knowledge representation that will then illustrate how this data can be combined, and more importantly, what the meaning of that data is when we do so. Now, of course, each one of those classes, when you in Stardog turn on our BI SQL feature, ontology classes turn into tables. You could also do the same thing with stored queries or shackle definitions. But in this case, everything within that model, from the stat nodes to the domain to the sensor series, all become tables. And that means we're delivering to those democratized citizen data users a series of tables that will be populated with that connected data, with the inferences as well. And so that investment of being able to put these descriptions into place is now going to pay off, as instead of having to essentially redo those calculations, the data scientist does it once and then the analyst does it once. We've codified it into reusable logic, and now we're enabling these additional use cases and user groups to take advantage of it. So looking at the data science workflow, we can do things like issue a graph query. And this happens to be within a Databricks notebook. It could be easily a Jupyter notebook. And the key thing here is that the graph queries, when inside the Spark environment with the Stardog Spark connector, return data frames. So here we're looking at, if you're not familiar with the graph query language, it's basically saying there's some airports. We're looking for Yellowknife, which is, I think, one of the most northern Canadian cities. It has a daily sensor value. In this case, we're looking for the date and the temperature. And this is just letting us explore the data set. We could easily do this in Stardog Explorer with the Visual Query Builder. But as the data scientist in this case is going to be looking at the different data sets and trying to interpret the meaning, being able to run the query and have at hand a data frame of which you can then manipulate allows them to very quickly move to the next step, right? So there's no extra code here in terms of cleaning up or fixing the frame. It's all driven off of a knowledge query that populates the frame, and then we can move forward from there. So with that in hand, we're going to combine the compliance rule with the weather series. And in this case, the engines are for airplanes, so the engine models. And we're going to do this to produce yet another frame. In this case, our frame will be the sensor series run, whether it was compliant or not, which engine model it represents, and then we're going to annotate it with the weather. Now, these rules are executed on the fly, so it is query time level inferencing. The joins you might look at this and say, well, where's the join? I don't see inner join or left join. And it's really expressing the connections of the data that you care about, right? My flight has some statistics. The statistics have an annotation. This will have a run with the flight ID that has an engine. The engine has a model, and so on. And this could also be done in Advanced Query Builder, but as we were going through the notebook example here, we started with the notebook. And this would just be one of lots of different queries that could be built, right? Another one could be comparing a pollution data set to engine performance. So with that in mind, we trained a model that looked at the sensor series from the 3 engines and came up with a predicted value. And we then wanted to compare how the different engine models fit those predictions. And by doing so, we issued the graph query. We then grab a data frame, and we can use standard, in this case, Python data visualization to plot that. And we see a couple of curves here. Now, these results are all stored in the graph. We have the stats nodes in the graph. We've also stored the predicted values in the graph. And so with the couple of different models and their predicted values at hand, we'll then run the dynamic time warping, which in the bottom right here is just like this fast DTW. And this will give us a distance. And it turns out that one of the profiles was a bit closer. Therefore, we can infer that that is a good representation of actually how the engines are going to perform in the field. So that's an example of time series, but that is one minor ribbon of capability, right? It's a pattern on how to deal with IoT or time series data that's going to be prominent in all sorts of ways within the manufacturing domain. And one of the things we wanted to look at was what would the model look like if we rounded that out, combining the IoT with incoming material testing, the manufacturing process and the equipment used in there, quality notes and warranty. And the epicenter here is, of course, material or the product. So coming soon will be a series of templates for these models. And as you can see here, this is but a subset, and we already have a pretty busy model. And so this was our first version of it. I'm sharing that with you today. The version that will be released compartmentalizes this, and they all fit together like a jigsaw puzzle, right? So if your first use case is around quality notes and warranties and stop shipment, you might only use that knowledge template. But if you then compare that to as operated and field information from IoT sensors, you would bring in that second one, and so on. And so these templates give a high-level representation of the different types of entities in a getting started manner. So it's not supposed to represent every company's potential quality note definitions, but it has enough on quality notes and deviations. It's fitting those manufacturing best practices as we've observed them across many clients, and distilling this down into what are those key entity and relationships that we see over and over again. So please stay tuned for more on that. I think that will be a topic for one of our later demo days. And then the different examples here, the digital twin, the time series, and bill of material, we hope to also make those knowledge kits. So when you go into Stardog Cloud, and as you're looking at the different knowledge kits available, each one of those will be individual kits that you can load into a database. And that includes not only the model, but a little bit of sample data and some queries to operate with it, right? So these are all kind of getting started accelerants that we can provide to move that solution up and, again, build that insight on a faster timescale. So with that, that concludes the presentation portion of this webinar, and we can open it up to questions.
Thank you, Al. Really appreciate it, the in-depthness. So we did have some questions being posted. If you haven't posted questions yet, feel free to go ahead and do that, either in the chat or in the Q&A. So I'll serve you up a couple of the questions. Someone asked if this solution requires Databricks.
Right. So Databricks is a good example. You do get value from the Stardog partnership with Databricks in terms of that catalog support, very quickly building, doing the mappings on how tables and columns turn into nodes and edges in the graph. But the pattern on how you combine the analytic with the knowledge model is generic. And our Spark connector, what we were using within the notebooks to run a graph query and turn it into a data frame, that's implemented against the Spark 3 API. So that will also work against any Spark cluster. You can also use PyStardog, which can produce Panda data frames. So it looks like we have another question here on how is this different than, say, using Neo4j. So we recognize that there are Neo4j instances out there within this space. Quite often they will address a single use case, but not really go much further. And the reason for that is Stardog provides not only graph query and graph data representations, but it allows you to map that to the variety of the different data sources. They don't have to be SQL data sources. They could be things like MongoDB. They could be unstructured data. And more importantly, it was that knowledge model that enabled us to start to compose and represent the rules in a data-driven way. And so that's something that you'd have to write as stored functions within Neo4j. It's just going to slow you down. And it's not going to give you the tooling around being able to represent things like ontologies to do that faster. We also have some material on our website on looking at how property graphs and Stardog compare. More recently, we've added edge property support to Stardog, so you can have what's known as RDF star and Sparkle star to add properties to edges. So another way to represent that time series data would be to use edge properties. Though at the end of the day, that's really just another statement within the graph. So I don't feel particularly compelled to force things into the labeled property graph model or the semantic model. In fact, if it's in the semantic model, then I'm thinking more about how do I group these different concepts together into different classes. And when I want to slice and dice my data in different ways, like adding in the cold weather support, I do that in the model, not by tagging the data or anything like that.
Correct. And I think I addressed that in the Q&A as well. We do have some resources on the differences between labeled property graphs and knowledge graphs. Knowledge graphs are based on RDF standards. You could find information on the web on that as well. But certainly a topic that we are interested in and do talk about a lot. So love questions like that. All right. So I see a couple more questions in both Q&A and the chat. Someone's asking about ontologies and how they're used. And then someone else is asking about how data is validated after inferences are made.
Okay, a couple of things there. So let's start with the validation aspect. You can add in the shackle definitions and apply that. That works with inferencing. So you can do the inferencing and then run the shackle. You can have shackle definitions that have further classes within them and run shackle with inferencing turn on. So that's all possible. That also helps identify places where the data doesn't quite connect the way you thought it did. And quite often we find this in what should be, say downlinks, but what you really find is some source might have uplinks. So the parent record, instead of referencing the child ID, instead the child ID record has a reference to the parent ID. And you want to knit that together properly so your queries and all the rest of it are not littered with, which direction did we pick on this one particular system. So shackle is a great way to find things like that. When we do our model-based system engineering talk, we talk about how we extend this back into the engineering side of it, where you can obviously think about things like a requirement that didn't get implemented, something that was in the design that didn't appear as a requirement, dead-end links or orphans, and how that is realized in the graph. And you can find things like that, as well as hotspots, especially on traceability. We all kind of refer like, why did we do this? So I did this because it was this requirement. So you can imagine that, especially in a hardware software solution space, quite often the hardware teams will all kind of point at one generic software requirement. And so you need to make additional hops to connect things to, really how they should be. So shackle is a great use case for that. What was the other question, Ingrid?
I think the other question was around ontologies, in that, how are they used in Stardog? And
right. So the ontologies, while you could have a Stardog database that had ontologies and data all together in one graph, what we typically recommend is to organize your ontologies into separate name graphs. So as I showed that kind of preview for our manufacturing templates, that was all within one named graph, but you could see that even that was too much. So we want to decompose those ontologies into different subdomains, and those different domains would appear in their own name graphs. And then the way you use those together, so you're not spending all your time thinking about which name graphs to include, you can simplify that with the name graph alias feature, which think of that as a macro that then expands to a list of name graphs or virtual graphs used to answer a query. And that alias can be also referenced in connection strings. So if you want to say enable your Tableau user base, but you definitely don't want them to think about which name graphs are in scope. Instead, you use the alias feature, you put that in the connection string, and then they are none the wiser, right? They're using 3 ontologies, 2 named graphs and a virtual graph, and they see that in this case as tables, and it's completely abstracted from them and managed in a centralized place. Oh, look, there's my friend Erlon. So Erlon asks, okay. What are some additional strategies around the time series, especially, should be virtual, should it be stored? And I'll say that what we talked about today was the pattern at the model layer. From a data management perspective, the series could be loaded into Stardog, but most likely not. Most likely that's going to sit in things like a data lake or a data lakehouse. And we are then going to elevate that up into the graph by providing the virtual graph definition. In some cases, especially as you start building aggregates, you might materialize a roll-up of that. So if you have, let's say we're doing flight data and we've got readings every second for a 2-hour flight, that's going to be a lot in your time series table. So from that, we might aggregate that and roll it up to every minute. And once it's down to every minute, well, that's going to be much smaller data. And from there, just for expediency's sake, we might just materialize that or keep a cache copy. I will say that the one thing I mentioned earlier about the pattern of being able to use the name graphs to your advantage to store the stats nodes in reference to the other nodes, that can also be this hybrid mode where you have done your stats roll up. You probably have something like a notebook or a process that's generating those, and those all are in reference to the actual series, which is probably sitting on the relational side that we're just doing virtual graph queries over. Because quite frankly, it's not going to be the individual sensor value that we care about. It's going to be those stats and rollups that are really going to fuel the insight, right? So we need to be able to understand these large series, and we do that with statistics, and we then want to combine that back into the knowledge model. Now, there will obviously be extremes for very long time series like the stock market and stuff like that, which, those are still going to present challenges, but there will be more strategies that we'll be sharing in days and weeks to come on how to deal with that. But this core pattern is one of the innovations that we've put together to kind of deal with this domain.
Great. I think those were all the questions we had on deck. So if no one has, oh, here we go. We got another question. All right, we got something in the chat here.
So the way we handle aggregation will be in a graph query. So we had a couple thoughts on this one. One thought was that we'd build a graph query that would materialize something called an instant or a moment, and then they would link together. So you have, instant to instant, so minute to minute. So you can always follow next. You'd have kind of a next pointer. And we compared that type of model versus just here's a sensor reading. It has a value data type property, and it has a occurs on data type property, which is a date. And the Stardog handling of date time and queries was actually very efficient. And there was not much difference between rollups that move to next edges versus just expressing it in a normal date time comparison function. So within the sample notebook, that is the tactic we took on this one. We're looking at other different types of time series, right? So this one happens to be relatively time boxed, right? Because it's about flights. It's only going to be a few hours. Even at the second level, that's not going to be a ton of data. So all these types of queries are still very, very efficient in that. We're looking at additional longer series, like 5 years of stock market data and how to represent that and query over that, and will we use the same strategies? And right now the answer is trending yes. There might be some different adjustments we might make for larger series, but they're going to be the same types of adjustments you make on larger graphs anyway, right? So as your knowledge graph grows over time, using the strategies we've talked about today in terms of compartmentalizing the models, compartmentalizing the data, introducing selectivity into how you do that is basically the key to keeping that good, efficient query time, even as your knowledge graph grows to, billions and billions of triples.
Thanks for handling that follow-up question, Al. Great. Well, with that, we're going to come to the end of the webinar. If anyone has any more questions, you can always reply. That is me usually in those emails. And if I don't respond, it means it went to spam or I didn't see it. So if you have any additional questions, I'll be sure to pass them along to Al. As noted earlier in the webinar, we recorded this. A copy of it will be sent to you. I'll also send along some resources that you can read further about these topics in our website. And hopefully when we have another webinar, you guys can join us as well. If you ever have any topics you'd like us to cover, feel free to let me know. Thank you so much for your time. Really appreciate it. We know it's the most precious commodity. And thank you to Al Baker again for speaking about this super interesting topic.
Thank you.
Have a great day, everyone.